Hi, welcome back. And today we are going to see about the EMF equation of transformer. So before moving into this topic, we will quick recall about the previous class of single phase transformer construction. So here the construction parts the transformer core. It is mainly made up of silicon steel, mainly to minimize the eddy current losses. And the winding of transformer, it has primary winding and secondary winding, or it is made up of copper to minimize the variable losses. That is nothing but copper loss. And the insulation, we are using the paper and transformer oil can be used as an insulation. And for cooling, we are using the oil, or it may be an hair. It may be enforced or it may be a natural system for the cooling. So on today we are going to discuss about the how the EMF equation can be generated, and we are going to approach a design thinking approach in this topic, and what is the real time applications and the assessment of this particular topic. Okay, so what is EMF equation? The EMF is nothing but electromotive force. So which is nothing but the EMF will be induced in the transformer winding, because we are giving the power supply only to the primary winding, but we are getting the output, we are getting the induced voltage in the secondary winding. It is based on the Faraday's law of mutual induction principle. Okay, okay. And so here we are applying the empathize. So why we need this EMF equation of single phase transformer? So what is the use? How it will relate to the practical application? How this will use in the design stage and to calculate the efficiency of transformer. Okay. So from this empathize, we are concluding some challenges. Okay, so how we can able to calculate the induced voltage in this secondary winding of transformer? We are giving the power supply only to the primary, where we are getting the output in the secondary. How it will be induced? How much it will induce? So according to what parameter the induced voltages get changing? Okay. So what about the flux density which is produced, and what is the size? What is the area of the transformer core, and what is the supply frequency we are maintaining in the transformer core, and how to relate the output with respect to the number of turns in the primary and secondary winding? So these are the some of the defined stage in the defined stage. Okay. Now we will go for the ideate. So how the EMF equation can be derived from the system? Okay, so now we can consider there are two limb. So here in the first limb, the primary winding is connected with the supply, and in the second limb, the primary secondary winding is connected with the load. Okay, so here we are generating, we are giving the input as AC supply. So if you are giving the AC supply, the produced flux in the primary winding, it also produces flux in the form of AC supply. So if the flux is produced in the primary winding, it has some flux at the maximum level. So that is nothing but pi m. So here the rate of change of flux at that is nothing but the rate of change of flux. Okay, so you can take the sine wave. The flux is maximum at the time of 90 degree. If you are taken as 90 degrees t, 1t, 2t like that, so the time it is in reciprocal of frequency. So instead of t at the time of 90 degree, we are multiplying 1 by 4f. So therefore the average value of EMF induced per turn, if for a single turn, how much will be induced means that is 4F. 4F into maximum flux. 4F into maximum flux. So this much amount of voltage which is induced per turn. So now we have to remember the form factor. The form factor is nothing but the RMS value divided by average value. So the RMS value can be calculated with respect to the root of area square divided by time period, and the average value can be calculated with respect to area divided by time. So from this, so for a sinusoidal waveform, the form factor is 1.11. The form factor is 1.11. So in order to determine the RMS value, to find RMS value, so which is equal to 1.11 into average value. So already we know the value is 4F pi m. So by multiplying the 1.11, we are getting 4.44 F into pi m. F into pi m per ton. So in single ton it produces an voltage of 4.44 F into maximum flux. If you are having n number of turns in the primary winding, you can multiply n1. If you are having n number of turns in the secondary winding, you can multiply the n2. So the final equation of the induced EMF E is equal to 4.44 F pi m into n. Okay, if you want to calculate the induced EMF in the primary winding, you can multiply the number of turns in the primary. If you want to calculate the output in the secondary winding, you can multiply the number of turns in the secondary winding. So from this we can able to derive the EMF equation. So from this equation, F is nothing but the frequency, the fundamental frequency. So in India, we are always maintaining the 50 Hz frequency. In USA, they are maintaining 60 Hz frequency. And N is nothing but number of turns. So N1 indicate the primary number of turns in the primary, and N2 indicate the number of turns. So according to our output voltage, we can able to vary the, and we can able to change the N1 and N2. And pi m is nothing but it is the maximum flux is produced in the transformer core. It is mainly based on the flux density and the area of the transformer core. And 4.44 is the constant, so it is in the form of 2 pi divided by root 2. It is in mathematical derivations. So this is a prototype. And so in the testing and evaluating stage, so the theoretical can be used, and for the laboratory can be used, and we can able to compare the accuracy between the theoretical and practical. So we can get the accuracy of 2 to 3% with the validations. So the main application of this transformer is mainly used in the distribution side, and also used for the mobile phone charger, laptop charger, to convert the 230 voltage into 5 volt, 10 volt, 20 volt, like that, and also it can be used in the DVD player, CD player, etc. So this is the summary. So in this image, finally this is an EMF equation. E is equal to induced EMF is equal to 4.44 F n into pi m. So we want to calculate in the primary, you can put this as n1. If it is secondary, you can put it as n2. Okay, so this derivation can be derived by using the Faraday's law and with the help of rate of change of flux and with respect to the average value and RMS value. So the component which are used is frequency, number of turns, flux density, and transformer area. Okay, so this is mainly used to calculate the output voltage of the primary and secondary windings. So this is a query challenge. Okay, you can think and answer in the comment section. So why is the constant 4.44 and not some other value? Okay, so you can see the voltage rating always 1.1 kV, 3.3 kV, 6.6 kV, 11 kV, 22 kV, 33 kV, 66 kV, 110 kV, 220 kV. So it is always in the multiplication of 4.44. So what is 4.44? Just you can think and put your answer in the comment section. So this is also an assessment question. So why do we use RMS value in the EMF equation instead of peak value or average value, etc.? So you can put your answer in the comment section. And these are the few references and online material for this particular topic. Thank you.